All right, so today we are doing 2 applications of integration, okay, and I'm going to do the best I can to demonstrate these for you, but it just might be a good idea to log on and ask about them. Okay, so we're starting with a function, okay, and I'm going from x equals a to x equals b. And what I want is the arc length. That is the length of this little piece of curve. Namely, if I were to lay a string all along it so that it matched up perfectly and said, okay, it went from here to here, and then take the string, straighten it out, and lay it against a ruler, what would be the length of that arc length? So, the idea is that I'm laying little pieces of string flat against it that are perfect lines, okay? So my slices are going to be these little flat diagonal pieces of line, okay? All right, so what am I really talking about? Let's blow this picture up, okay? A single slice is this little diagonal line, okay? The curve is kind of going next to it. And what do? How do I find the length of a straight line? I use the Pythagorean theorem. This side length, whoops, I forgot that was still on. This side length is delta x, the distance between 2 x coordinates. This side length is delta y, the distance between 2 y coordinates. Okay, so now I'm going to apply the Pythagorean theorem to find this little arc length. Arc length is traditionally referred to by the letter s. So based off the Pythagorean theorem, s will be the square root of delta x squared plus delta y squared. Okay. All right, now I'm going to do some interesting arithmetic to this. I'm going to multiply this by delta x over delta x. Only the way I'm going to write delta x on the bottom is as the square root of delta x squared. And I can do this, of course, because I can always multiply something by 1. All right, now I'm going to distribute this into both pieces. Delta x squared divided by delta x squared is 1. Okay. Delta y squared divided by delta x squared is delta y over delta x quantity squared. And then I have a delta x on the outside. Okay. This is where I'm deriving my formula for the arc length of the slice. So, the arc length of y equals f of x on an interval from a to b is then defined by, well, how do I always solve a problem? I cut up my arc length into slices. I approximated each slice with a straight line. Now I'm going to add them back up again and take a limit, which amounts to turning it into an integral. Now, when I take a limit, delta y and delta x become dy and dx. I'll refer you to our discussion from section 3.9. Delta x becomes dx. And what am I adding up from? From the point A to the point B. So, this is our formula for arc length. Okay. Now, this is if I sliced it with respect to x. I could have done a very similar thing for a function x equals g of y on an interval from c to d. Only the difference here would be that since I wanted everything in terms of y, I would have divided by delta y over delta y to turn it into this. Notice this integral is identical. Basically, I just switched the place of all the x's and y's. Now, I'm going to give you a warning. These integrals are always very hard. The large majority of them are going to require a technique that we're not going to learn until chapter 8. Okay. At this point, you have 2 hopes for how this integral is going to work out. Number 1 is if you can do a u sub, where u is the inside of the square root, and it will work by some miracle. Number 2 is if you can rewrite the inside of this square root as a perfect square, so that the square root and the perfect square will somehow cancel each other. That's usually much easier, but it requires some algebra, okay? These problems are not going to be quick. So, let's do our first example of calculating arc length. Okay. All right, before I go to my formula, I'm going to compute dy dx. Okay. This is, of course, the derivative of y. So that gives me x minus 1/4 times 1 over x, or x minus 1 over 4x. Okay. All right. I'm also often going to take the time to clean up the inside of the square root before I put it inside the square root and inside the integral. So 1 plus dy dx quantity squared will be 1 plus this thing I just computed, quantity squared. Okay. I'm going to FOIL that last part to give me x squared minus 1/2 plus 1 over 16x squared. I can combine the 1 and the 1/2 to give me a plus 1/2. Now, notice, when I FOILed out x minus 1 over 4x, quantity squared, I got this. The thing I now have is identical to this one, except for this minus sign has become a plus. Well, the minus sign came from here. Okay, so this will actually factor as x plus 1 over 4x, quantity squared. Okay, this is actually a very common trick that will happen with these types of arc length problems. So now the arc length will be the integral from 2 to 4 of the square root of x plus 1 over 4x quantity squared, because that's what this equals. The square root and the square cancel, and I'm left with this integral, which I luckily know how to take. The 1/4 comes along for the ride, and then 1 over x gives me ln of x. And I don't need to worry about absolute values when every number in the case is positive. Plug in top minus plug in bottom, and I get this arc length. Okay. I did warn you they were bad. Okay, let's do another example. So, first thing I do is find dy dx. This is a tiny chain rule. Okay. Notice, please, that I now have a negative exponent. Okay. X over 2 to the negative 1/3 is the same as 2 over x to the positive 1/3. I really only care about the fact that the x is in the denominator because my interval includes the number 0. And I cannot plug in 0 to this derivative. Okay. You cannot use the arc length formula if the function is not defined and its derivative is not defined on the entire interval. So, does this mean we give up? No, it does not. It means we switch everything into the other variable. So, I'm going to take this equation and I'm going to solve for x. So x is twice y to the 3/2. Okay, I need to change my interval. If x is 0, plug it into this equation. 0 over 2 is 0. 0 to any power is 0. If x is 2, 2 over 2 is 1. 1 to any power is 1. So now I'm on this interval. This time I want dx dy. That is the derivative of x with respect to y. Multiply the 3/2 down, gives me 3y to the 1/2, not a negative exponent, and I do not have the same problem I had when it was in terms of x. Now, 1 plus dx dy quantity squared is 1 plus 3y to the 1/2 squared, or 1 plus 9y. All right, so my arc length is going to be from 0 to 1, the square root of 1 plus 9y dy. All right. This is technically a u sub where I'm letting u be this inside. However, the only thing that it's going to do is introduce a factor of 9, we can deal with that without writing out the u sub. Okay, so I have the inside raised to the exponent plus 1, divide by the new exponent. The derivative of the inside is 9. I have to divide by that as well. Evaluated from 0 to 1 gives me this result. Okay. Okay, we're going to do one more example of arc length before moving on to our second application. All right, as always, I'm going to start with computing dy dx. This is a chain rule. Derivative of ln is 1 over its inside times the derivative of secant, which is secant tangent. And of course, the secants cancel, and I'm just left with dy dx's tangent. So 1 plus dy dx quantity squared is 1 plus tangent squared. Now, at this point, you should be saying, that looks familiar. It is a Pythagorean identity. 1 plus tangent squared is equal to secant squared. And I prefer that because then, when I take the square root, it will clean up. So my arc length is the integral from 0 to pi over 4 of the square root of secant squared. The square root of secant squared is, of course, just secant. Okay. Antiderivative of secant, ln of secant plus tangent. And then I plug in top minus plug in bottom and get ln of the square root of 2 plus 1. Okay. By the way, this particular antiderivative, the antiderivative of secant, is going to keep on coming back and back and back. I suggest memorization. And I don't suggest that often, so I must really mean it. All right, this is our